In this video, I will present a paper called Self-Stabilizing Byzantine-resilient Communication in Dynamic Networks. So first, let's present the setting of the problem. We consider a communication network that can be represented by a graph, and in the general case, if a node wants to communicate with another node, it has to send its message through several intermediary nodes. So if all nodes behave correctly and all correctly forward messages, this is not a problem. But in a world where networks grow larger and larger, we must take into account the fact that these nodes are likely to fail. So it can be a crash failure, where some nodes just stop functioning, but it can also be much more annoying than this. So there are many possible models of failure, but here we will consider the worst possible model of failure, the Byzantine model, where a failing node can have any arbitrary behavior. In other words, to show that a system is robust to Byzantine failures, we have to show that there exists absolutely no strategy for Byzantine nodes to lead the system to an incorrect behavior. And the interest of assuming Byzantine failures is that it encompasses any other possible model of failure, by definition. So if a system is resilient to Byzantine failures, it is also resilient to any type of failure, which is a very strong security guarantee. So here, the problem we consider is the problem of reliable communication. For any two correct nodes P and Q, if P sends a message M, well, first, we want to ensure that Q actually receives and accepts this message. This would be the liveness condition. And we also want that Q does not accept a false message pretending to be from P. That would be the safety condition. For instance, P could send a blue message, and Byzantine nodes could send a red message pretending to be from P. So to have a reliable communication network in the presence of Byzantine failures, we have to satisfy these two conditions. So a first work on this topic considers the connectivity of the communication graph, that is, the minimal number of disjoint paths between any pair of nodes of the network. So two paths are disjoint if they have no node in common, except of course the first and the last node. And the famous result is the following. To have reliable communication in the presence of up to k Byzantine failures, that can be anywhere in the network, well, it is necessary and sufficient for the network to be 2k plus 1 connected. So between any two nodes P and Q, there exist 2k plus 1 disjoint paths. So I will skip the necessary part, but the sufficient part is pretty simple here. So we can represent two nodes P and Q with 2k plus 1 disjoint paths connecting them, and with k Byzantine failures, well, you can corrupt at most k of the 2k plus 1 paths. So the message of P is forwarded along the k plus 1 correct path, and then Q just has to wait until it receives k plus 1 times the same message from P. And with at most k corrupted paths, we will never be able to have more than k false messages pretending to be from P. So the safety condition is satisfied here. So this result was later generalized to dynamic networks, that is, networks where the topology can change with time. So the model of dynamic graph is the following, which is very standard and general. So there is a presence function, indicating whether or not a communication channel between two given nodes is present at a given time t. And there is also a latency function that gives an upper bound on the time necessary for a message to cross a given communication channel. And then we can define the notion of dynamic path, that is, a dynamic sequence of nodes and communication channels enabling a message to transit from a node P to a node Q after a given time t0. And then it becomes a little bit tricky, because in static networks, there is an equivalence between minimal cut and connectivity. So the connectivity is the number of disjoint paths between any two nodes, as we have seen previously, and the minimal cut is the number of nodes we need to remove to disconnect any two nodes of the network. And in a static network, these two numbers are the same. This is called Menger's theorem. But in dynamic networks, this is not true anymore. So you can have examples of dynamic networks where the minimal cut is not equal to the connectivity. So to generalize the result to dynamic networks, a solution was to reformulate everything in terms of minimal cut. So more precisely, in terms of dynamic minimal cut, that is, the minimal number of nodes you need to remove to cut all dynamic paths between any two nodes. So this leads us to the necessary and sufficient condition for reliable communication in dynamic networks. Min cut of din pq0 must be strictly greater than 2k, where din pq0 is the set of dynamic paths between p and q starting at time 0. And there is an associated communication algorithm that is guaranteed to work whenever this condition is satisfied. So in the following, we call this condition the RDC condition. RDC for Reliable Dynamic Communication. And now, I can finally present the contribution of the paper. We present an algorithm solving the same problem, that is, reliable communication in a dynamic network in the presence of Byzantine failures, but, in addition, this algorithm is self-stabilizing. So what do I mean by that? So basically, a self-stabilizing system is a system that can recover from any arbitrary number of transient failures. What is a transient failure? Well, each node follows a given algorithm that could be considered as hardwired, but in many cases, this algorithm will use some variables, and the memory slots storing these variables can be initially corrupted. And in addition, the communication channels can initially contain an arbitrary number of arbitrary corrupted messages, if we consider that their buffer are another form of memory slots. So a distributed system is self-stabilizing if it always eventually satisfies a given property, so for instance reliable communication, in a setting where the initial content of local variables and communication channels is totally arbitrary. And here, we want to do this in addition of the permanent Byzantine failures that will not go away. So what we try to do here is called multi-tolerance, that is, tolerating several types of failures. So here an unlimited number of transient failures and a given number of Byzantine failures. So here we present an algorithm that ensures reliable communication in a very hostile setting. Unlimited number of transient failures, permanent Byzantine failures, and the topology changes with time, which is pretty good in terms of robustness. So of course, like previous algorithms, this algorithm is only guaranteed to work when a certain condition is satisfied. So what is this condition? So without transient failure, we had to satisfy the aforementioned RDC condition. And now, with transient failures, we have to satisfy the following condition. The RDC condition is always eventually satisfied. So what do I mean by that? Well, previously, the condition was that for any two nodes P and Q, min cut of din PQ0 must be strictly greater than 2k. And now, the condition is that for any two nodes P and Q and any time t0, min cut of din PQ t0 must be strictly greater than 2k. So at this point, you may wonder, why should it be always eventually satisfied? Isn't it sufficient to just be eventually satisfied? Well, actually, no. In the paper, we prove a first result. If the RDC condition is just eventually satisfied, and not always eventually satisfied, well, the problem of reliable communication is impossible to solve. So in this setting, just eventually satisfied is not enough. So to show this, we consider a toy example with only three nodes, P, Q, R, and we assume that there is no Byzantine failure here, and P wants to send a message to R. So in this setting, the RDC condition simplifies as follows. There must exist just one dynamic path between P and R. And let's assume that there exists an algorithm solving our problem under this condition. So first, let's consider a first scenario S1 of x, of which x is a parameter. P sends the message M1. Step 1, edge E1 appears, then disappears. Step 2, edge E3 appears, then disappears. And during this time, T receives the message X from Q. Note that this can happen for any message X because we assume transient failures here. And therefore, the communication channel between Q and R can initially contain anything. So in this scenario, as edge E1 appears, then there exists a dynamic path from P to R, and therefore, as the algorithm supposedly solves the problem, then R eventually accepts M1. Okay, and let's call y the state of R between step 1 and step 2. Note that y is independent of x because R has not interacted with Q at this point. Now, consider a second scenario S2. R is initially in a state y. It can be in any arbitrary initial state because we assume transient failures. That's part of the problem. P sends M2. Step 1 prime, edge E2 appears, then disappears. Step 2 prime, edge E3 appears, then disappears. So here again, there exists a dynamic path from P to R. Thus, again, as the algorithm supposedly solves the problem, R must eventually accept M2. Let's call X prime the message sent from Q to R during step 2 prime. Okay? And now, finally, let's consider scenario 1 with parameter X prime after step 1 and scenario 2. What is interesting here is that, from the point of view of R, what happens is exactly the same in both cases. R starts in state Y, then receives X prime from Q. Thus, according to both scenarios, R must accept both M1 and M2, which are two different messages, which is a problem. So what we have shown here is that, in a setting with transient failures on a dynamic graph, it is not sufficient to assume that the RDC condition is just eventually satisfied, because it can lead to a situation where a node accepts two contradictory messages from a same sender, and therefore, we cannot have reliable communication. And we didn't even have to invoke Byzantine failures here. Okay, before going further, let's restate the problem properly. So we have a setting with up to k permanent Byzantine nodes, which identity is unknown to the correct nodes, of course, a dynamic graph, and we also assume that no matter which algorithm is executed by correct nodes, well, to the extent that this algorithm manipulates some variables, well, the initial state of these variables is assumed to be arbitrary. And the communication channels between nodes can also contain an arbitrary number of arbitrary messages, which are sent but not yet received. So this accounts for transient failures. So each correct node P has, at minimum, a message PM0 that it wants to broadcast to other nodes, and a set Px to store accepted messages. So Px will contain tuples of the form Qm, and when Qm belongs to X, this means that P considers that message M was sent by node Q. So in other words, that M equals Qm0. A short remark here, these PM0 messages are not subject to transient failures, because if they were, well, it would be impossible to ensure any form of reliable communication, per definition, because all messages would be arbitrary. By the way, this is a simplified way to state the problem, but one could also consider that each node decides to send new messages later in time. The reasoning would be the same. So the problem is the following. We want to find an algorithm to be executed by correct nodes such that, given this setting, for any two correct nodes P and Q, we eventually have the two following properties. First, there is no M' distinct from PM0 such that PM' belongs to Qx, that is, eventually we do not have any false message in the X sets, so here PM' would correspond to a false message because P did not send M'. So this would be the safety property, that is, what we want to avoid. And the second property to be eventually satisfied is the following. PM0 belongs to Qx, that is, Q eventually accepts the correct message from P. So this would be the liveness property, that is, what we want to achieve. And in the paper, we present an algorithm solving this problem. So first I will give a very high-level description of the algorithm. So one part of the algorithm is similar to a previous algorithm considering the same problem without transient failures. That is, we broadcast the messages through every possible dynamic path, and each time the message is passed to a neighbor node, we register the identifier of the node. So we try to keep track of the path. And before accepting the message, a node checks if the various paths attached to this message are compatible with the RDC condition. So that would be sufficient without transient failures, but with transient failures, well, for instance, it is possible that a false message has already been accepted. Or, in a more tricky way, that enough false messages have already been sent to have a false message accepted later in time. So, in the previous algorithm, the formalism of messages was the following: SM capital S, where S is the sender, M is the content of the message, and capital S is a set registering the nodes that forwarded this message. And here we add a number alpha. So here is the main trick. The algorithm is designed so that false transient messages are stuck with the value of alpha they initially have, whatever this value is. And then, if correct nodes keep broadcasting this message with increasing values of alpha, and if we give priority to messages with the highest value of alpha, then the correct messages are eventually accepted. So, of course, Byzantine nodes can still broadcast messages with arbitrarily high values of alpha, but several rules of the algorithm ensure that this does not happen. So each correct node U has the following variables: a counter U alpha, as seen previously, that can only increase, a memory set U omega, that stores all messages received by U without discrimination. So, as we have seen, messages of the form SM capital S alpha, a set U ax 0 that stores pre-accepted messages. So basically, messages that check the RDC condition, as in the previous algorithm. But, as we have seen, this is not sufficient, and we need more guarantees to accept them, a condition that would involve the parameter alpha. Okay, so now let's go in more details. So the algorithm itself consists in 5 rules. The first rule is that each node regularly increases its counter alpha from time to time and adds the following tuple to its set omega. So a tuple with its own identifier, its own message, an empty set, and its current value of alpha. So to initiate the broadcast of a message along several dynamic paths, as we will see immediately. The second rule is to send the content of U omega to its current neighbors whenever the content of omega changes or the set of neighbors changes, so that we do not miss any opportunity to explore a given dynamic path. So basically, omega contains all the information U has to broadcast. The third rule is that whenever U receives a tuple SM capital S alpha, well, first, it adds the identifier of the neighbor sending it to S. So this is how the path is registered. Then store it in omega. And as omega changes here, of course, it will also send it to neighbors, according to the previous rule. Rule number 4 looks a little bit more complicated, but basically, what we do here is to check if some collection of received tuples check the RDC condition. More precisely, that there exists a message and an associated sender node such that the path attached to the corresponding tuple checks the RDC condition, and if so, the message is added to P-Ax0, the set of pre-accepted messages. And finally, rule number 5. So first, we introduce a function count that counts the number of different values of alpha associated to a given message. And the idea is that, for a given node identifier S, we consider that the message sent by S is the message with the highest count of alpha. The underlying idea is that, as the actual node S keeps sending its message with increasing values of alpha, its count will eventually be greater than any other count caused directly or indirectly by transient failures. So in the correctness proof, among other things, we have to show that the combination of transient and Byzantine failures does not allow to keep broadcasting a given false message with increasing values of alpha. So to conclude, we provided the first self-stabilizing and Byzantine-resilient algorithm for reliable communication in dynamic networks and proved its correctness. And to go further, one could, for instance, consider more probabilistic settings. So, for instance, random positions for Byzantine nodes, that is, each node may have a given probability to be Byzantine, or maybe random evolutions of the dynamic graph. One could also consider permanent failures at the level of communication channels. So, for instance, communication channels regularly and randomly dropping messages. And finally, an interesting open question would be to consider the time and space complexity of solving this problem, and see if sub-optimizations could be made with regards to this time and space metrics. And thank you for your attention.